Massachusetts Institute of Technology just cracked open an AI black box that the entire industry has been running blind for 5 years. What they found inside explains why every AI model keeps getting smarter. But it also reveals something the billion-dollar labs are not advertising: the exact point where smart stops. And it is closer than anyone is saying out loud. The billion-dollar bet with no explanation. Every major AI lab on Earth right now is running the same strategy. Build a bigger model, spend more compute, use more data, get smarter results. It has worked every single time for 5 years straight, and the companies doing it have collectively spent hundreds of billions of dollars on it. Here is the part that should make you stop and think. For all 5 of those years, not one of them could actually tell you why it worked. They knew it worked. The pattern was undeniable and consistent. Double a model's size and performance improves by a predictable percentage. Double it again, and you get the same jump again. Researchers gave the pattern a name, scaling laws, and the entire AI arms race was built on top of it. Bigger models, bigger budgets, bigger results. Every generation of every major system follows this exact trajectory. But the mechanism underneath, the actual reason why size translates to intelligence, was a complete mystery. Hand-waving theories and educated guesses were the best anyone could offer. And that gap between knowing something works and understanding why it works is exactly where danger hides. Because if you do not know why the strategy works, you have no way of knowing when it will stop working. MIT just closed that gap. And what they found in the process is something the industry needed to know and probably did not want to hear. What is happening inside an AI model? Before you can understand what MIT found, you need to understand what is actually happening inside a language model when it processes text, because it is not what most people picture. It is not a database lookup. It is not keyword matching. It is not autocomplete on steroids. What a language model is doing when it reads a sentence and predicts the next word is fundamentally geometric. Every word the model knows gets converted into a coordinate, a point floating in a mathematical space with thousands of dimensions. Think about GPS for a second. 2 numbers, latitude and longitude, are enough to pinpoint any location on the surface of the entire planet with precision. 2 dimensions. Every location on Earth, no ambiguity. Language models use the exact same logic, but scaled to a level that is hard to visualize. Instead of 2 dimensions, they use 4,000 or more. Every word in the vocabulary becomes a unique point in this enormous space. The geometry encodes meaning directly. Words that are conceptually related end up sitting close to each other in the space. Eiffel and Paris cluster together. Eiffel and sandwich are far apart. The model learns these positions during training, adjusting every coordinate until the geometric relationships between words mirror the meaningful relationships between concepts in the real world. When it predicts that the Eiffel Tower is in Paris, it is not recalling a memorized fact. It is navigating geometry where the answer is written into the distances between points. More dimensions means more axes of meaning, more precision, more nuance, which is the first hint at why bigger models are smarter. But it is only the surface of the story, the assumption everyone got wrong. Here is where the story gets interesting. A model with 4,000 dimensions is trying to store 50,000 different words simultaneously. 50,000 unique points crammed into a space geometrically designed for 4,000. That is a severe overcrowding problem, and it has to be solved somehow. For years, researchers assumed they knew how models handled it. The theory was called weak superposition, and it made intuitive sense. Models prioritize. Common words, the is and, get stored accurately because the model sees them constantly during training. Rare words, technical jargon, obscure proper nouns, unusual vocabulary get compressed or effectively dropped. The model keeps what matters most and quietly sacrifices the rest. Under this theory, bigger models work better simply because more dimensions means more storage. Fewer words get dropped. Vocabulary coverage improves. Accuracy increases. Clean, logical, sensible, and completely wrong. When researchers looked inside actual language models to verify this assumption, the results contradicted it entirely. The models are not throwing anything away. All 50,000 tokens are stored in the same 4,000 dimensional space at the same time. Everything is in there simultaneously, words piled on top of each other, representations sharing the same dimensional addresses, patterns overlapping with other patterns. MIT called this strong superposition. No word gets its own clean private location in the model's memory. Everything shares space with everything else. The information is all present, but compressed and overlapping in ways that create a problem-weak superposition never even considered. This is why AI lies to you with confidence. Strong superposition explains something that has frustrated users of AI systems since the beginning: confident hallucination. The model tells you something completely false with total certainty. No hesitation, no qualification, just a wrong answer delivered as established fact. People assume the model is guessing or making things up. That is not what is happening. The information the model needs almost certainly exists somewhere in its compressed representation. The problem is that overlapping storage creates interference between related concepts. Think about it this way. If you store the Eiffel Tower, the Empire State Building, and Big Ben in the same compressed dimensional space, their representations mix together. The signals overlap. When the model tries to retrieve a specific detail about the Eiffel Tower, it occasionally pulls out a fragment from the overlapping Empire State Building representation instead. The answer that comes out is wrong, not because the right answer was never stored, but because the storage architecture scrambles retrieval when representations share space. For years, this interference was treated as an unavoidable side effect of building AI at scale, an annoyance to manage rather than a mechanism to understand. MIT changed that. Because they discovered the interference is not random. It follows a precise mathematical law. When 50,000 tokens are stored in 4,000 dimensions, the interference between any two representations is exactly proportional to 1 divided by the model width. Double the model width from 4,000 to 8,000 dimensions, and interference drops by half. Double it again to 16,000, and it drops by half again. MIT tested this on real models, and the measured error rate fell at exactly the rate the equation predicted. Not approximately. Exactly. Why scaling works AND where the wall is. This one mathematical relationship explains scaling laws from first principles for the first time in the history of AI research. Bigger models are not smarter because they learn fundamentally different things. They are not developing new reasoning abilities that smaller models lack. They are smarter for one specific reason. More dimensions means less interference between overlapping representations, which means more accurate retrieval of information the model already has. That is it. The entire scaling advantage reduces to interference reduction through dimensional expansion. The companies spending hundreds of billions of dollars are not guessing. The improvement is real and it follows quantifiable geometry. But here is what MIT's math also tells you. Interference reduction through scaling follows a diminishing returns curve. Each doubling of model width cuts interference in half, but you need the next doubling to cut it in half again. And the next. And the next. The compute cost of each successive doubling grows exponentially. The capability gained from each successive halving of interference shrinks. At some point, you are spending enormous resources for improvements too marginal to justify the investment. The wall is not a cliff where scaling suddenly breaks. It is a gradual slope where each dollar of scale buys less than the dollar before it. And MIT's equation tells you exactly how steep that slope is and where on the curve the industry currently sits. The answer is not comfortable. What happens after the wall? The most important implication of this research is not what it says about the current strategy. It is what it opens up beyond it. If strong superposition interference is the actual bottleneck, if models make mistakes because everything is crammed into overlapping dimensional positions, creating signal confusion, then the question is whether interference can be reduced in ways that do not require adding more dimensions. Training models to compress information more efficiently using architectures specifically designed to minimize overlap could in principle produce the same accuracy as a much larger model at a fraction of the compute cost. A smaller model built with interference-aware training could outperform a conventionally trained model twice its size, not because it has more storage, but because it uses the storage it has more cleanly. This is where the research points. Not just building bigger, but building smarter, engineering around the interference problem rather than throwing more space at it. Whether this direction produces a genuine breakthrough in the next few years or takes a decade to develop is not yet known. What is known for the first time is the precise mathematical shape of the problem. And knowing the exact shape of a problem is most of the work toward solving it. The entire AI industry built on a pattern nobody could explain. MIT explained it. Bigger models cut interference between overlapping word representations, and that is the complete reason scaling works. The same equation that explains the advantage also draws the wall. Diminishing returns, exponentially rising costs, marginally shrinking gains. The race to build bigger is not over, but the math now tells you exactly where it ends. Drop a comment telling us whether you think the labs will hit that wall in 2 years or 10. Check the end screen for more A1 breakdowns sitting there waiting right now.